I'm going to do a couple stories actually, and they relate to quite a few talks that I had went to. They were on exoplanets. Exoplanets, planets that are going around other stars other than our own sun. And in fact, I listened to or went to three different exoplanet talks here. And the reason that there was quite a few of them is that we're celebrating the 20th years of the discovery of 51 Peg, which was the first planet discovered around another sun-like star about on October 20 years ago. And so my two stories relate to exoplanets, and in particular, discoveries made from the Kepler mission. And so in one of the talks, specifically talked about Kepler, and so I kind of wanted to, as a little primer to the stories, go through the Kepler mission. And so the primary uh, purpose for Kepler was to look at what we call transit photogrammetry to detect Earth-like planets going around other stars. But it actually revolutionized the stellar astrophysics field as well, because since it was making such precise measurements looking for these transits, it also makes very precise measurements of the stars that these planets go around as well. Now, it was launched in 2009, and it went for about 4 years until two of its reaction wheels gave out and can no longer point the telescope, but it has now been repurposed into a mission that's called K2, which I'm going to tell you about, which was one of the discoveries was made from. So in its mission, it is actually staring out into space utilizing a camera that has 85 million pixels on it. And the 95 million pixels compared to your maybe 10 million pixel camera are laid out into this kind of curved array here that sits at the focal plane of this particular telescope. You might see that these little corner arrays don't have much things other than these little squares over here. And the purpose of these things were to have stars in these particular locations so that Kepler could stare at the same point in space continuously. And it did so for 4 years, taking data essentially every 30 minutes without blinking. A few times it blinked. Where it stared in space was in this region in the constellation of Cygnus, and I just showed you the focal plane there. That's how it was laid out on the sky. And so it was looking, and this spot was very carefully chosen, where we didn't want to look right into the plane of the Milky Way here, but because stars are too crowded, or we have a lot of gas and dust that's interfering with our data. We don't want to look too far out of the Milky Way galaxy because then the stars aren't dense enough to see. So this was kind of an optimal spot so that it could look at these 150,000 stars. And what it was looking for were transits of planets across the star. Now, we have seen transits in our own solar system. How many people saw the Venus transit not too long ago? Okay, we saw a few. And this is what we observed. Now, and then here is another one where we've got Mercury over here transiting the sun. Now, from our position looking at the sun, we see the full transit. We see the planet's disk actually transiting the sun. Kepler does not see that. It just sees the combination of the light of the planet and the sun. That happens, all it sees is a dip in brightness when the planet transits in front of it. So here is, say, a Jupiter transiting that planet, and when it does so, you see a dip in brightness when it transits. And in the case of Jupiter, Jupiter is about 1% the size of the sun. The dip in the spectrum or in the light is actually 1%. So it's a direct measure of the size of the object there. So if you know the size of the star, which we can figure out by looking at that particular star and knowing what kind of star it is, you can figure out the size of the planet itself. Now things get a little bit more difficult when you try to actually measure the Earth, which is considerably smaller, seen as this little dot right here. So in this case, it's only 1/100% the size of the sun, and so therefore you see Dip in brightness, it's only 100%. Sorry for the mic here. I'm trying to figure out where to hold it. It keeps cutting. Well, that's where I think it often goes out. So I haven't quite figured out. Well, we've had this problem before. So anyway, I'll try to vary the distance here to see if it gets a little bit better here, but it's always kind of disconcerting. So when you see only a 1% or a 0.01% dip in the brightness, you start to get buried into the noise of how accurately you can measure the brightness of that particular star. And this is why Kepler was really the only one that spacecraft that could do it, because it was up in space. From the ground, we can't measure to that exquisite of sensitivity to see little dips like that. So Kepler's main focus is to see how many Earth-sized planets there were out there. So here is actually the results of its 4 years data as of January 2015. They are still crunching the numbers on all of that data. And in fact, the data processing continues to get better and better so they can squeeze out more and more planets. And what you see in this plot here are the relative size of the planet that is a candidate here, in which there are now 4,175 candidates here, the relative size in relationship to the Earth's radius. So here's the Earth at 1 Earth radius right here, up to Jupiter, which is on the order of 10 Earth radiuses here. And then this is the orbital period in days, and in other words, how long it takes to go around its parent star. So you can see that a lot of these have much shorter periods than our own Earth, which is 365 days, which is out over here, which we have seen some candidates that are out here in this regime. Jupiter actually would be way off to the right here, because it takes 5 years actually for Jupiter to go around, and Neptune would be even further off to the right here. But anyway, you see that there's quite a few planets that we have discovered that are on the size of our Earth. And in fact, we've seen a whole bunch of planets that are in this kind of intermediate zone between Earth and Neptune. And one of the interesting things is that is thought to be the most common sized planet, and yet we do not have one in our solar system that is of that type. Now, as they continue to crunch the numbers, they're hoping to populate more down over in here to get more of the Earth-like planets. Now, the reason it takes longer to get over to here is because of that orbital period. In order to confirm that you had a planet there, you have to see a transit. You have to see a transit after its year, and then you have to see it again and see that the periodicity between those is exactly the same value. So if you're going to detect our Earth, you're going to need at least 2 years in 1 day to, if you got really, really lucky, to actually have observed that. So anyway, so they're looking still at that data to populate that. So the blue and the yellow, they don't have too much significance. These are when they announced this January 2015 release here. The blue ones are the previous candidates, and these ones that they added to it. So you can see they're adding more and more to this part of the curve, which we're interested in too. And so the next final release, I guess, or whatever it'll be, as they continue to look at that data, and they're not getting any more of that data. They're no longer staring at that point in the sky. Hopefully, we'll populate even more in that region. And of these kind of 4,000, about 1,000 of them have now been confirmed as planets. Just to kind of show you where we were 20 years ago, this is where the few planets were being discovered. And those were being discovered by a different technique called the radial velocity techniques, where you were actually looking at the star and watching it move toward you and away from you under the influence of a planet that was going around it. And so those are the first detections that were made, and you can see Kepler has really added quite a bit to those. Not necessarily the ones these are all probably from transits from Kepler, but this is the general domain that we were measuring before. And at that time, they were finding these kind of Jupiter-sized objects more because the technique was more sensitive to those Jupiter-sized objects. But as you look at the actual population of the planets that have been found by Kepler, you'll see, like I was saying, these more Neptune-sized objects are the more common ones. But there's what we call a selection effect in here as well. These Earth-sized ones are very, very difficult to measure. They're buried down in the noise. So we still have to develop the techniques. So if you fold into the fact that you're not detecting a bunch of these, we believe this curve continues to rise so that there are actually more Earth-like sized planets even in this particular bin here. But in general, this is where we think somewhere in there it's peaking. And it's like I said, it's interesting that we do not have an analog of that in our own solar system. And you why we believe that it's going up here because these ones here are much harder to detect. And so they're still in the noise. So you can do statistical analysis to say how many of these have I missed in this particular study and account for that. And so they have pretty big error bars, but it's believed that it's still that this curve is continuing to rise here.
What percentage of the candidates are false?
I went to a talk on that. I think they believe the majority of them are real planets. So some of the things that can cause false positives are things like eclipsing binaries. There's another star in there. So there's other techniques that you can go through to try to confirm that whether it is or is not a planet. And then some we don't quite know. So that's another thing about the data processing as we continue to look at this data. Okay, so one of the very interesting things that Kepler was trying to do, though, was also trying to find Earth-like things that were in what we call the habitable zone. In other words, that one region around the star where we think liquid water would exist. So for a sun-like star like our solar system, our Earth is, of course, in the habitable zone. Venus is on the kind of the inner edge of the habitable zone, and Mars is actually in the habitable zone on the outside. But there's other reasons. Just because you have a planet in the habitable zone doesn't mean you necessarily going to have life on it. In the case of Mars, you end up having not enough of a mass to hold in the atmosphere, so it lost its atmosphere. But the basic concept here is that the hotter stars have habitable zones that are further away from the star, and the cooler stars, which are the most abundant stars there are in the universe, have them actually much closer, and Kepler measures quite a few of those transits of these cooler type stars. And just to kind of go through some of the systems that it had here, this projector is actually not working as good as I thought it was. I can't quite see where the habitable zones are. So this is one of the first planets that were detected, Kepler 22 system, where we had a planet within the habitable zone. But we can see that the planet was quite a bit bigger than that of the Earth. And these are done for our solar system to scale. Other things that Kepler found were these multi-planet systems, just like our own. So here's Kepler 62 that had 5 planets within it. They're orbiting closer to its star, but it was also a cooler star, and so therefore some of these were actually in the habitable zone. And the two systems that are probably most like Earth that Kepler has discovered to date are Kepler 186, which is a planet that's very close to the size of the Earth, but it's orbiting in the habitable zone of an M dwarf, of one of these cooler stars here. And then we have Kepler 452, which is very much like a solar planet here, but it's a little bit bigger than that of Earth. And that's so here is kind of the family of the small planets that it's found so far under these the M stars, the K stars, and the G stars. The G stars being like our Earth that Kepler has so far discovered. Now, one of the problems with Kepler is it can't get any much more detail on these planets. It was more of a census thing, trying to figure out how many kind of planets that we had out there. Any Star Trek buffs out there? Okay, I'm an early Star Trek watcher, and so actually this particular episode, Balance of Terror, is one of my favorite ones. There was an episode 1, but McCoy actually says to Kirk, in this galaxy there's 3 million Earth-type planets. I think call them M-class planets in the vernacular of Star Trek there. But McCoy wasn't too far off. Based on the statistics of Kepler, there are about 20 million Earth-like planets in our Milky Way galaxy. And in fact, the other statistics that that Kepler revealed is that there's about a planet for every star there is in the Milky Way. So we've got 100 to 200 billion planets within our own Milky Way galaxy. Okay, so Kepler, this is just a schematic of how Kepler looks out into our own Milky Way galaxy. This is artist's conception of the Milky Way. It was looking off, like I said, above the Milky Way plane, just a little bit off into a direction, kind of along a spiral arm. And its kind of search space was about 3,000 light years away or out there, but it was looking at every star in that particular cone. And so, like I said, it was monitoring about 150,000 stars within that cone. The problem is those stars are too far to find out any other information about those stars in general. They're just too far away. So we really, to go to the next step in exoplanet research, we really need to look at exoplanets that are orbiting much closer to us. And one of the things we need to disentangle is that Kepler has found a lot of these objects that are smaller than Neptune but are bigger than Earth, which we call super Earths. But we don't, like I said, have an analog in our own solar system, so we don't know, are these gaseous? Are they rocky? And so we can figure out the size from Kepler, but we can't figure out their density unless we figure out their mass. And we can't figure out mass until we look at objects that are closer that allow us other techniques to find out their mass. So Kepler broke, and it looked like it was done, and that nothing else could be done for it. And anyway, it has been reborn by a bunch of clever engineers and figuring out how to actually point it. Now, one thing I learned in this little telecon, it's called K2 because of the mountain K2. Not because it's Kepler 2 or Kepler 2 using 2 reaction wheels, but K2 being a challenge. Okay, so that's where it actually got its name. And so what happened to Kepler is it has these reaction wheels on the spacecraft. And you don't power a spacecraft by firing thrusters. You have these little reaction wheels that you spin up or slow down, and you can get the telescope to point in any direction. Well, you need at least 3 of them in operation to actually point the telescope. So when they lost 2, they thought they were done. So some clever engineers came up with this concept to use the solar cells that are collecting energy from the spacecraft, which, can you kind of see this outline of blue over here in there? That blue right there is actually the solar cells there, and they were using the solar wind pushing on the solar cells to balance the telescope. So the solar cells would always have to be, that point of the solar cells be evenly pointed toward the Earth. And if you did that, you could use the solar wind as an extra reaction wheel. And that's what they were doing. And in fact, they figured it out that it could actually be done. And then they came up with this way of actually a new observing plan. And to do it, here are the solar cells that are right there. They found that they had to orbit where they kept the spacecraft looking at another field of view here, off in this direction here, and they could go for about 85 days before they could no longer get the benefit of this kind of even push from the solar wind, and then they have to reorient the telescope in this direction and go there again, and then reorient it again. So now it doesn't have the capabilities it had before, where it could stare in the same point in space continuously, but it could stare there for 85 days or so and look at other fields of view. And since it's now done its census work, this is great work because it knows how to detect planets. It knows there's lots of planets out there, 1 per every star that's essentially out there. So now it can look at a totally different kind of region of space. And in fact, since it has to be in this alignment, it's looking out in the ecliptic of our, which is the orbit of which our Earth goes around the sun. So it's looking out in that region of space, and so it's going to be able to sample a whole bunch of different points in space and discuss and look at a lot of different objects, in which my story will be related to one of those kind of objects that we can now look at. So here is the plan for K2, where that's that array looking out at different parts of the sky for the 2014. The story that I'll talk about today was in the 2014 data, so those are the 3 fields for that. Then 2015, it'll look at that. You can see the galactic plane here. So there's going to be an area where it looks really close to the galactic plane. And so it's going to be looking at a whole bunch more objects there. And so here's an example, a couple places it's going to look. It's going to look in this star forming region here. It's going to look at the Hyades and the Pleiades clusters that are here. The Hyades is a much bigger cluster of stars here in the Pleiades. So we're going to be looking at young regions, old regions, all sorts of places, and some of the other bright stars that potentially are closer to us that ultimately represent higher value targets. Now, don't worry about all this stuff, but basically they think it's going to be discovering about 100 rocky planets in the habitable zone per year in its new studies. Okay, on to the story of one of the stories that I've got here for today. So this is an article that came out about a disintegrating minor planet transiting a white dwarf. And by a minor planet, we mean something like on the order of an asteroid, or at the largest, maybe something the size of our largest asteroid series, around a white dwarf. So I need to explain what a white dwarf is. Stars grow old and die because they burn up all their nuclear fuel at their core. Our sun will do the same, and our sun will have the fate where it will actually turn into a white dwarf. And before it does that, it'll evolve into this red giant phase where it'll puff up much bigger. In the case of our sun, this will happen in about 5 billion years. It'll puff up to about the size of Earth's orbit, so about 100 times bigger. So we may be inside a red giant one day in 5 billion years. And then as it does that, the last burning embers of its core, which are down in the center of the star, it basically blows off its surrounding layers. It loses about half its mass or a third of its mass in this process. And the last remaining remnant of this is what we call the white dwarf. It is now purely carbon and oxygen, because the hydrogen is burned to helium and the helium is burned on to carbon and oxygen. And it's about the size of the Earth. So it's a very, very small object, but it's really, really hot when it comes out of this planetary nebula. So it can be like on the order of 30,000 degrees when it's first born. And then it's dead at that point, and it just continues to cool. In this planetary nebula phase, it's not there very long, maybe 10,000 years or something like that, where that hot ember there basically ionizes the gas that it had thrown off into space at an earlier time. So that was the object that one of these that Kepler 2 was actually looking at and saw in the data a transit signature. And so it looked at this particular point in the sky for 85 days. Okay, so to look for transits, they do something they call a Fourier analysis. If you've ever seen a spectrum analyzer for like sound or something to say what kind of frequencies, do I have high voices, do I have low voices, or whatever that are in that, if you do an analysis very similar to that of the 85 days, you can pull out if there's some periodicities in there. And so these little peaks that you see here are actually things that were happening at a particular period. So this one was happening at 4.5 hours. Okay, so something was periodically dimming the star every 4.5 hours. And so they found 6 of these little peaks, and then you can take that data for the 85 days and just bin them in that sequence. In this case, 4.5 days, in this case, 4.55, 4.6, 4.8, or so forth, and just add up the data and see what signature you have. And so for the largest one here, this A one here, was at 4.5 days, here, very close to 4.5 days, if you look at that number. This is the profile that it actually had. So there's a little dip in brightness that is occurring for this white dwarf. So and then you see that these are lesser and lesser magnitudes here by how much they're actually dimming, but there appears to be kind of like 6 components in this particular white dwarf. So what is going on? What is actually causing this? And in fact, you can look at more detail. Let's look at that one component there for the excuse me, the 4.5 hours. there. You can see as the mission went on, here's through the kind of 80 days here, that transit was changed its profile over time here. So you can hardly see anything here. And that other data set I showed was just basically adding all of these up. And it changes its depth and its profile. Once they noticed this, one of the things that they've been trying to figure out with white dwarfs is that white dwarfs, I said there should only be carbon and oxygen. But when they look at the spectrum of the white dwarf and stuff, they often find heavier metals. And that the abundance of these heavier metals, anything heavier than helium, are consistent with what we would see in, like, minor planets and asteroids and things like that. They would have an abundance ratio like that. So where are these things actually coming from? So it's often been speculated that because the other heavy elements, if there were some there, should sink to the base of the white dwarf in a very little time, on the order of 1,000,000 years or something like that. So, which not a little time for us, but anyway. So why do we actually see some of that in the spectrum? So it's been speculated that we actually have some asteroids or something like that that are continually disintegrating and feeding the surface of the white dwarf. And so that is the number one theory, is what's actually going on with this. And then they started doing some measurements from the ground, and they found some very interesting results. And in this case, these are some. It's harder to do in the ground because you can't measure it continuously. So they looked at it with a 1.2 meter telescope, and I think these are only like a 0.4 meter telescope. There's two color dots, and so this is at the primary frequency of 4.5 hours. And you can see for this, we saw a transit and then another transit 4.5 hours later here. But look at the depth in the brightness here. It went from 1 being the brightness of the white dwarf down to about 60% of it. So it blocked off 40% of the light from this star. So the star is small; it's only Earth size. So we're talking about a smaller object, but that's a big depth in brightness. So you need something that's at least 40% the size of the white dwarf to cause that. And here was another location there as well. And there's a bunch of other interesting things in this data, in the sense that these were out of phase based on the Kepler data. These were taken after the Kepler data. So by out of phase, it means that if you kept projecting this 4.5 days forward in time, it changed. It's still 4.5 days, but it's shifted a little bit. So we're trying to figure out what exactly that could be. And so the hypothesis is it really is, something maybe on the order of series at maybe 6 objects, or maybe a single object that is disintegrated into 6 or so, and that it's rotating so closely that it's being tidally kind of disintegrated, so that it has kind of these sporadic episodes of blowing some dust out into space. And so this object is very, very small. So as an object, couldn't cause the dip in brightness, but if it blew material out into space, it could produce a cloud that would indeed create that kind of signature for these objects. And in fact, one of the things about the signature, if you look at it, is it's asymmetric. So you have the transit occur here. If it was just a planet, it would come up and come back down, but you see this kind of long tail over here, which is due to what we believe is this kind of outflow from the disintegrating object that's leaving a tail as it continues to go around, creating a bigger object that's creating that dip in brightness in the case of the ground-based measurements that they actually had. The interesting thing is, how did that object get there? So that's the thing that's, a little bit befuddling. They're trying to look at the details of how would you get that object to that space. It's orbiting very, very close to the white dwarf. One of the theories is it was a planet that was in the solar system at one time, just like our Earth, and that when it went to red giant phase and things like that, you could get some of these orbits that could be basically tossed in toward the planet. But then at this point, it's now orbiting close, and the orbit has been circularized. It's no longer like an elliptical or comet type orbit. Something had to get it there, and then it had to then have a mechanism that could get it in a nice circular orbit.
Maybe a rogue planet.
Well, it wouldn't. It'd have to be a planet that was from one of from this system. So anyway, it's very interesting results. They haven't been able to do this ever before. This is the first transiting planet of a white dwarf, and it's because Kepler's ability to see these closer white dwarfs in its old Kepler field, it would not, the white dwarfs in this field would be too faint as they were too far away for it to actually have made this particular measurement.